Hi, this talk is for a general audience. I want to explain why the neutrinos are so important in the unified theory and how close we are to understanding it with experimental evidence. So what is a unified theory? Well, in physics we mean a theory that encompasses all the known interactions. There are 4 types of interaction: electromagnetism, the nuclear forces, of which there are 2, strong and weak, and gravity. Without gravity, we have the standard model of particle physics. So the mathematics of the unified theory, which we usually call quantum gravity, should reduce in different regimes to the known interactions that we had before, which is the standard model and the classical theory of gravity, otherwise known as general relativity. So what is a theory anyway? There are 3 important aspects to a theory. There's the mathematical formulation of it, the principles behind it, and the experimental results that either prove or disprove it. Let us illustrate this with dark matter. There are 2 big theoretical hypotheses for dark matter. There's string theory, which is mathematically very complicated, which says that dark matter is just new kinds of particles that we haven't observed before. The second theory is that we should modify even classical Newtonian gravity to understand the apparent appearance of dark matter. So which one of these 2 possibilities is the correct one, would you think? The answer is neither, because any real unified theory will reduce in different ways to both of these possibilities. Now you might think this is a clear contradiction, but I will explain to you how this works. First of all, the mathematics of the unified theory encompasses the mathematics of string theory, but the particles of string theory are not there, because the principle that we should start with new particles is not the correct principle. So we end up with a modified form of classical gravity, as we hypothesized in the alternative, coming from the principles of quantum mechanics as it happens. Now, classical gravity has no quantum mechanics in it at all. So what we do is we consider the quantum observer within our fundamental principles, and we get rid of dark matter and replace it by quantum inertia as a foundation for mass. So in string theory, the correct thing to say is that the extra degrees of freedom in quantum gravity in higher dimensions are there, but they're not particles. And in quantum gravity, in the full theory, we say that mass is now generated from a cosmological principle, and this is where neutrinos come in. So what is a neutrino? So inside the nucleus of an atom, we have protons and neutrons. And the shell of the atom has electrons, so that the positive charge of the protons balances the negative charge of the electrons. Now both neutrons and neutrinos are neutral particles. So hang on a minute, you say, where was the neutrino? Well, in radioactivity, so when a uranium atom decays, what happens is that inside the nucleus, a neutron is turning into 3 particles. It turns into 1 proton, 1 electron, and 1 antineutrino. Now the proton charge and the electron charge balance out so that charge is conserved going from the neutron to the 3 particles at the end. The neutrino is there to conserve something else, which has to do with whether a particle is a part of a nucleus or not. So the electron needs to be balanced by the antineutrino. This basic decay is the foundation of what we call the weak nuclear force. Now the strong nuclear force involves quarks, which are components of protons and neutrons. And pretty much everything in particle physics is built from these particles. But in the standard model, neutrinos have to be massless, just like a particle of light, a photon. They must be massless. And yet experiment tells us that all neutrinos have a small mass, a very small mass, much, much less than an electron mass or a proton mass. In fact, the mass is so small that we're going to use it as a natural scale in nature. Now this is interesting. There's a long history in particle physics of focusing on high energy scales, because that's where things tend to happen in particle accelerators, and that's related to black hole generation, which we know has something to do with gravity. But there's also a fundamental low energy scale. And here is the miracle. That neutrino scale, which we can split up into 6 different rest masses for neutrinos, corresponds exactly to the present day temperature of the microwave background radiation that we see in our sky coming from all directions of the cosmos. And that's because low energies are really the same thing as large distances. Here is the proper map of the cosmic microwave background radiation. And you see the temperature is not uniform everywhere. That's represented by cold blue patches and hot red patches. But the characteristic statistical spectrum of radiation is a very fundamental one, and its peak occurs at a specific temperature, which corresponds to one of the right-handed neutrino masses. Now let me stress that in string theory, this coincidence between mass and CMB is completely impossible, because masses are supposed to be pretty well random after a 14 billion year evolution. But we are quite happy to throw out the Big Bang cosmology because astrophysicists have been telling us for a while that it doesn't fit a great deal of data, such as early star formation and other things. And we're going to start with our 2 scales, our low energy scale and our high energy scale, and generate mass from the massless theory which we understand well. But before we could do that, even though it's quite a simple thing, we had to know the right mathematics for the standard model of particle physics in the 20th century, and that has taken us the last 20 or 30 years to figure out. So experiment is telling us to start with a completely new principle for mass generation. Now the large scale, which is the scale of our observable universe, as observed by us, that is closely related to this neutrino energy which defines the CMB temperature. As observers, we're pairing that large scale with a very high energy scale which governs the behaviour of the matter that we know about around us. We pair those two to determine the localization of energy, which is what mass is. In the unified theory, we're using ribbon pictures to represent the fundamental states of the particles that we already know about. Why do we do that? We do that because the mathematics we need is the mathematics of quantum logic, which describes observational statements that we might make to determine an experimental outcome. Now, quantum logic is a large extension of classical logic. And you might remember from high school, classical logic is about sets. Here we have 3 sets in a Venn diagram, A, B and C, and what we care about is where A intersects B, where B intersects C, and where A, B and C all intersect, and so on. And that's a logical statement, A and B, or if I don't include the intersection, I have A or B, and as we all know, that's how computers operate. But the point is that we've represented the logic with diagrams. And the claim is that these diagrams underlie the basic geometry that we naturally need to describe space-time or any other geometry in physical problems. And in 3 dimensions, we can have things that not. But we didn't start with 3 dimensions. We started with quantum logic and asked ourselves, what kind of statements do I need to make to say something about the world in our laboratory? We started with not pictures, but not real numbers. And this is the thing about quantum logic. It underlies all the classical geometry that we usually use in physics and in other sciences. Unless you happen to work on the theory of quantum computers, in which case this is just your cup of tea. Similarly for superconductors in condensed matter physics. This branch of mathematics is called category theory. Its axioms exist in every dimension, and they involve ribbons or perhaps polytopes. Here's one picture of an important polytope called the icosahedron. To begin with, everything is discrete because that's quantum mechanics, and it's discrete. We're looking at these pictures without thinking about the geometry of the ambient space. And then when we look at the algebras that are naturally attached to these structures, we find simple elements of sacred geometry, and we shouldn't be surprised by this. Here I have the Seal of Solomon, which has a point at the centre representing the 72 names of God, and the 6 points on the outside, which to mathematicians represents a symmetry group for quarks, for instance. The most natural way to add numbers to these geometries is to start first with the counting numbers, 1, 2, 3, 4, and so on, and then not long after that we strike the golden ratio, although the golden ratio is a limit of ratios of Fibonacci numbers. So we are using infinite dimensions already quite early on. But anyway, all these nice geometries which people love to study now have a very solid interpretation in quantum logic. Now, why does this sundial keep popping up? Remember that one of the foundational principles in quantum mechanics going back to the 1920s is Heisenberg's uncertainty principle, which says that to make an energy precise, we cannot know anything about time. So the localization of energy to create mass is very closely connected in basic quantum mechanics to the idea of timelessness. And outside of the boundary of what we can observe, so on large scales or also on small scales, everything is effectively massless. We treat particles as being massless often in particle accelerator experiments. Something with the wavelength of the universe has no mass. So this is a principle called quantum inertia, which is already well studied by engineers, in fact, although not theorists. Yes, engineers like models of quantum inertia. They're not using this mathematics, but they are interested in building spacecraft using the quantum vacuum. The quantum vacuum is what we've been talking about all along. Thank you for listening today.